Reasons why we use numerical solutions. Okay, that includes the fact that there are certain differential equations which cannot be solved using the analytic method. Okay, secondly, for real life processes, sometimes it is extremely slow to count on analog solutions or manual computations. Okay, hence for the need for numerical approximations to functions. And we looked at one method, which is the Euler's technique. And we said there were other methods like the Taylor series method and the Range-Kutta method. Okay, so today we're going to look at the Taylor series method, and if time permits us, we also look at the Range-Kutta technique. Okay, so before we continue, if you have any questions on Euler's technique you want to ask, because we'll not come back to it. Yes?
We are giving to solve.
Yes.
We are going to solve Z graph or...
You are given the interval.
Yes.
So T is over the interval, for example, here 0 to 1. Yes. So you have to move from one end to the other end.
So we get the end.
Yes, yes. Unless otherwise, I ask you maybe to approximate, find y at maybe T of 0.5. 0.5 means you move about 5 steps from 0, 0.1, 0.2, 0.3, 0.4, 0.5, then you stop. Okay? Else you have to get to the end, because approximation is over that interval.
So when we draw the graph?
You don't need to draw the graph. Yes. Yes. Yeah.
From 0 to 1.
Yes.
11 times.
Yes.
So if we have to draw the graph, for example, we have to 11
Yes. So you have 11 coordinates. X, Y, X, Y. Yes. Please, somebody is asking a question. Someone is asking a question. Yes.
Does the value of the y change within the f of x, y? Like for instance, here we have 0 to minus 1 over 2. Will the 1 change?
Yes. So you see, y is defined in terms of n. Okay. So if your n changes to 1, this becomes y2. Here will become y1. You understand? So anytime yn changes, y will also change. Are we clear on that? Okay. So let's take off. Taylor series, we've all seen what Taylor series expansion is about. Okay. So usually the Taylor series, the general Taylor series expansion about a given point H is always approximated using what? Y at x naught plus the change, whether delta or h times dy dx, okay, evaluated at a given point, plus h squared over 2 d square y dx squared evaluated at a point, plus it keeps going to h raised to the power n over n factorial, the n that's the n derivative of y over the x at n evaluated at the various points. Okay, but however we cannot differentiate to so many orders. Okay, so usually we truncate the approximation. So basically, what we do is we use the first number of 10, depending on the order that is given. Then you truncate the expansion, which means you're only going to make use of the first section, which is the approximation formula. Okay. Then the error or the truncated error is given by the order formula. Okay. And this whole thing will depend on the given order of it. Okay. So, for example, when you pick the first Taylor series expansion, okay, you realize that it's going to be y at x naught, h of dy dx. Are you getting it? H over 1 factorial is the same as h dy dx, okay, plus the error of truncation, which is your big O rotation over there. Are you getting it? So if we have to take off the error this way, then we are left with this term. And if you look at this carefully, y at x naught plus h of f prime at x naught y naught is what? What formula is that? Y at x naught plus h f prime or f at x naught y naught is what? The Euler's formula. Okay, so the Euler's formula is just the first order Taylor series approximation method. Okay, in other words, we approximate at the first order. First order means first order of differentiation, and then all other terms have been classified as what? Error or truncated error. Do you understand? Okay. Very good. So in general, if we are given any order of expansion for the Taylor series, then in general this is what we're going to use. So depending on the order given, you truncate the approximation. Are you getting it? So assuming if it is first order, then everything here becomes error. Are you getting it? So you differentiate to the first term. If it's second order, you differentiate to the second term. Do you understand? Yes. If it's third order, you differentiate. So you differentiate to the number of terms what given. So we're going to solve the same question which we tried today, okay, using the Taylor series technique. So this time and you always need to be given an order, okay? So here we're going to use Taylor series, okay, with n equals to what? Let's say 4. Okay? Very good. If that is the case, then we are saying that we have to find the first derivative, second derivative, third derivative, or fourth derivative, and then evaluate at the given points. Okay? Before we come and find y1. You understand? So what you do is, already you've been given the first derivative, t minus y over 2. Okay? If you like, you will want to write it like this, t over 2 minus y over 2. Okay? Then we have to find the second derivative. So we're going to solve the same question which we tried today, okay, using the Taylor series technique. So this time, and you always need to be given an order, okay? So here we're going to use Taylor series, okay, with n equals to what? Let's say 4. Okay? Very good. If that is the case, then we are saying that we have to find the first derivative, second derivative, third derivative, or fourth derivative, and then evaluate at the given points. Okay? Before we come and find y1. You understand? So what you do is, already you've been given the first derivative, t minus y over 2. Okay? If you like, you will want to write it like this, t over 2 minus y over 2. Okay? Then we have to find the second derivative, which is going to be what? When we find the derivative of t with respect to t, what do you have? 1. 1. Okay, that's 2. Minus, when you find the derivative of y with respect to t, what do you get? Y prime over 2. So once we have y prime, this is going to give us this minus y prime is what? Y prime is what? T minus y over 2. You get it? So you can choose to expand this later. If we should expand it, let's just expand it. That will give us half minus what? T over 4 plus y over what? 4. Are you with me? Yes. Then we find y prime prime prime. That's the third derivative. This will give us negative 1 over 4 plus what? 1 over 4 y prime. So that is going to be negative 1 over 4 plus 1 over 4 into brackets t minus y over 2. Okay, then we can expand again to get what? 1 over 4 plus what? T over 8 minus what? Y over 8. Are you getting it? Then we find the fourth derivative. So the fourth derivative gives us y and b is what? T, the 1 over 1 over what?
Minus 1 over 4.
It's 1 over 8, you know, so
yes.
T over 8, so you get 1 over 8 minus y prime over 8, right? Which one we expand? We get 1 over 8 minus y prime is t minus y over 2. So this will give us 1 over 8 minus t over 16 plus y over 16. Are you following?
Yes.
Put it down. Write it down. Yeah, so these are the four equations which we are going to use for the evaluation, but we are not done yet. Okay, we need to evaluate, okay, the various derivatives at the given points. Okay, so since we are going to look for y1, now we're going to look for the first coordinate, y1, which means your n has to be 0. You understand?
Yes.
If n is 0, then you get y1. Okay, so if n is going to be 0, then it means that the first evaluation, the first point, let me play this side. The first point will be y prime evaluated as what? x0, y1. The initial point was 0, 1. Is that also?
Yes.
So then you substitute it here. This will be 0 over 2 minus 1 over 2, so which is negative half. Okay? Then y prime prime 2 will be the same, okay? So that will be 1 over 2 minus what? 0 over 4 plus what? 1 over 4. So that is half plus this, which is 0.75 or what? That's 2 over 3 over what? 4. Okay. Then the third one is y prime 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 S0 y equals to 1. Gives us what? Negative 1 over 4 plus 0 over 8 minus 1 over 8. What gives us this? Okay. Then we do say for y4, so we have x at 0, y at 1. That should give us 1 over 8 minus 0 over 16
plus 1 over 16.
1 over 16. This is 2 over 16, so we get 3 over 16. So the next step is to substitute the evaluated points into the general formula. Okay. And, so our general formula is so we know n is equal to 0. So y1 is equal to y0 plus h times what? y1 evaluated at the given point, okay, plus h over 2 y prime plus h over 3 factorial y prime plus h over 4 factorial y prime. Okay, so we just substitute those values. So y1 is equals to this y naught was 1 plus our step size was 0.1. Y prime is what? Negative half plus 0.1 over 2 factorial. Then y2 prime is what? 3 over 4. Y2 is it negative or 3 over 4? Plus we have a step size 0.1 over 3 factorial. Then the next value there, negative 3 over 8, negative 3 over 8 plus 0.1 over 4 factorial times 8 over 16. 3 over 16. Yeah, so do the calculation for me. Give me the final answer. For your answer, what did you get? 0.11. Okay, so you have to complete the solution, okay, at home as an assignment.
Thank you, sir.
So what I'll do is maybe I'll post the same assignment on Libas. Yeah,